Piping Vibration Flow Induced Turbulence, Understanding Causes and Impacts of Pipe Vibrations. Introduction to Piping Vibration, Significance and Risks. Piping vibration is a critical issue in process industries because it can lead to fatigue failures, leaks, and catastrophic ruptures. These failures pose severe safety hazards, environmental risks, and economic losses due to downtime and repair costs. Vibration-induced fatigue is often overlooked during design stages because most piping codes focus on static analysis rather than dynamic behavior. However, operational data from offshore and onshore facilities indicate that vibration accounts for a significant percentage of hydrocarbon releases and pipework failures. Understanding vibration mechanisms, especially flow-induced turbulence, is essential for engineers to design robust systems and implement preventive measures. The consequences of ignoring vibration include accelerated wear at welded joints, small bore connections, and supports, which can compromise structural integrity. Therefore, proactive assessment and mitigation strategies are vital to ensure reliability and safety in piping systems. Understanding flow-induced turbulence, definition and mechanism. Flow-induced turbulence refers to the chaotic and irregular fluid motion that occurs when fluid flows through piping systems, particularly at high velocities or near discontinuities. Turbulence generates fluctuating forces on the pipe walls, which act as broadband excitation sources. These forces originate from eddies and vortices within the fluid, creating dynamic pressure variations that transfer energy to the pipe structure. The severity of turbulence depends on factors such as Reynolds number, fluid properties, and system geometry. While straight pipes exhibit turbulence due to boundary layer effects, the most significant turbulence occurs at locations with abrupt changes in flow direction or area, such as valves, tees, reducers, and short radius bends. This mechanism is critical because even small energy inputs at natural frequencies can cause resonance, amplifying vibration levels and leading to fatigue damage over time. Common sources, characteristics, and energy distribution of turbulence. The dominant sources of flow-induced turbulence in piping systems include partially closed valves, short radius or mitered bends, tees, reducers, and process equipment that disrupts flow uniformity. These components create localized regions of high kinetic energy, which is distributed across a wide frequency range. Although turbulence is broadband, most excitation energy concentrates at low frequencies, typically below 100 Hz. Lower frequencies correspond to higher energy levels, making large diameter and flexible pipes particularly susceptible to vibration. This energy excites low-frequency vibration modes, often causing visible pipe movement and even oscillation of supports. Understanding the frequency characteristics is essential for engineers to predict vibration behavior and design mitigation strategies. For example, increasing pipe stiffness or altering support configurations can shift natural frequencies away from dominant turbulence energy bands, reducing the risk of resonance. This diagram illustrates the fluid dynamic behavior and associated energy distribution when flow enters a T connection, highlighting the turbulence-induced kinetic energy concentration. On the left, the fluid velocity profile shows streamlines and velocity gradients as fluid transitions from the main run into the branch. The color variation, from blue at low velocity to red at high velocity, indicates significant acceleration and directional change at the junction, which creates shear layers and vortices. These abrupt changes in flow direction and velocity generate localized turbulence, particularly near the intersection of the branch and main pipe. On the right, the kinetic energy plot quantifies this effect. With color contours representing energy intensity, the highest energy zone, depicted in bright yellow and red, occurs immediately downstream of the T intersection, where turbulent eddies concentrate. This localized energy concentration is critical because it acts as a broadband excitation source, predominantly at low frequencies. This diagram presents the relationship between turbulent kinetic energy and excitation frequency, illustrating why flow-induced turbulence predominantly excites low-frequency vibration modes in piping systems. The vertical axis, plotted on a logarithmic scale, represents kinetic energy expressed as dynamic pressure, while the horizontal axis shows frequency in Hz Hc, ranging from 0 to 100 Hz. The curve demonstrates a steep decline in energy as frequency increases. At very low frequencies, near 0 to 5 Hz, the energy is extremely high, several orders of magnitude greater than at higher frequencies, indicating that most turbulent energy is concentrated in the low frequency range. Beyond approximately 10 Hz, the energy drops significantly, and by 50 to 100 Hz, it approaches minimal levels. The oscillations observed in the mid-frequency range reflect localized flow instabilities and harmonics, but their amplitude is negligible compared to the dominant low-frequency content. This distribution is critical because low-frequency energy can couple with the fundamental natural frequencies of piping spans, causing visible displacement and high dynamic stresses, whereas high-frequency excitation from turbulence is generally insignificant. The diagram underscores the importance of considering low-frequency vibration risks in piping design and support strategies to mitigate fatigue failures. Consequences of turbulence-induced vibration, impact on piping systems. Flow-induced turbulence can have severe consequences on piping systems. The fluctuating forces generated by turbulence lead to dynamic stresses that accelerate fatigue damage, particularly at welded joints and small-bore connections. Over time, these stresses can initiate cracks, which propagate under cyclic loading, eventually causing leaks or catastrophic failures. In addition to fatigue, turbulence-induced vibration can loosen supports, damage insulation, and cause fretting at contact points. The risk is higher in systems with thin-walled pipes, long unsupported spans, or inadequate bracing. Furthermore, vibration can transmit to connected equipment, amplifying structural issues and increasing maintenance costs. In extreme cases, turbulence-induced vibration has led to unplanned shutdowns and environmental incidents. Therefore, understanding its impact is crucial for implementing effective design and operational controls to maintain system integrity and safety. Preventive measures, design considerations and mitigation strategies. Preventing vibration caused by flow-induced turbulence requires a combination of design improvements and operational controls. Key strategies include reducing fluid velocity by increasing pipe diameter or using parallel lines, which lowers turbulence intensity. Flow smoothing techniques, such as employing long-radius bends, swept tees, and flow straighteners, help minimize abrupt changes in flow direction. Selecting valves with high recovery factors and streamlined trims can reduce turbulence downstream of control points. Additionally, proper support design is critical. Supports should be placed near turbulence sources like valves and bends to limit vibration amplitude. Increasing pipe stiffness through thicker walls or composite wraps can also mitigate dynamic response. For existing systems, installing viscous dampers or vibration snubbers may provide temporary relief. Ultimately, integrating vibration considerations during the design phase is the most effective approach to ensure long-term reliability and safety.